Hello, everybody. This is Paul again, back with another fast tutorial. Today, we're going to talk about creating an aircraft specification file. So this is the tutorial number 3 in a big multi-part series. So if you haven't seen tutorials 0 through 2 yet, make sure to check those out. So this video is going to get into creating an aircraft specification file. So in the previous videos, we just learned how to run fast by calling an aircraft specification file an emission profile function. So now we're actually going to take a deeper dive into what makes up the aircraft specification file. And so what I've done is I've taken the liberty of opening example.m already. If you're following along and you need to find it, go to the aircraft specs package, open it up, and example is right there. And that's what we have on my screen here. So similar to the main function, like we saw in the previous video, we have a very similar function header. We have the function call, who wrote the function, when it was updated, a description of the function, the inputs, and the outputs. So for all the aircraft specification files that are shipped with FAST, there are no inputs, and there's only one output, which is the aircraft structure. And we call it the aircraft structure because it is a struct in MATLAB, and it contains all the information about the aircraft's design parameters, the requirements used to define the design. It also contains information about the run settings, how you are going to configure FAST to size your aircraft. And so we'll take a deeper dive into those substructures in this tutorial. So the one thing that I also want to draw your attention to before we get started looking at all of the aircraft parameters is that I'm not going to have time to go through all of the inputs that we provide. I'll give a high-level overview of the groupings, but I'm not going to go into super great detail for each one. Otherwise, this video would be an hour long, and that's no fun for anyone. So what we've done is in each package, we've put together another README file. So if you open this one up, similar header to all the other README files. And then this one provides an overview of the aircraft specification package. And in section 3, it has a list of variables that you can input to FAST. Now you'll notice this is a very long table, but each of the variables has its name, a description of the variable, the units of the variable, as well as a default value if applicable. And we'll talk about that if applicable in a minute. So as you can see, we have a bunch of different aircraft parameters and settings that you can input, 70-something of them right now. I'm sure there will be more to come. But you'll notice that this is a rather lengthy list. And well, a few videos ago, Paul, you said that there were only like 4 or 5 inputs we needed to run fast. And that is 100% correct. All you need is 4 or 5 inputs. But we give the user a lot of flexibility to define additional ones as well. And the reason we can provide the user this flexibility is that one of the distinguishing features of FAST is that behind the scenes, there is a historical aircraft database with over 400 different aircraft and over 200 different engines. So what this allows us to do is use regressions to quote unquote fill in the blanks. So all of the information that the user doesn't provide, either A, gets filled in by a regression, if it's some sort of design parameter or performance parameter, or B, gets filled in with a default value. So that's how we get away with prescribing a few variables and coming up with a design. The regressions do a lot of the work. So now that you're aware of this README, and I highly recommend you take a look at it, even though we're going through this tutorial, it'll provide a lot more information than what I'm going to. So now that we know about the README file, let's jump back into the example. So you'll notice in all of the aircraft specification packages, we group the variables by some higher category or discipline, you could say. So our top level aircraft requirements are the entry into service year, the aircraft class, whether it's a piston, turboprop, or turbofan aircraft, and the number of passengers that you're going to carry. And in this example file, you'll notice a big required next to all of the variables that are required to be input. So for example, since the entry into service year is not required, we can leave it as NaN or not a number, and FAST will assign it a default value. However, you can't, you need to provide a aircraft class because FAST will size it differently, whether it's a turbofan or a turboprop. In turbofans, we have a thrust to weight ratio, but in turboprops, we have a power to weight ratio. And we need to know the number of passengers you're flying, otherwise we can't run the regressions. Some other performance parameters that we include are the takeoff speed, the cruise speed, takeoff altitude, and cruise altitude. We also require you to provide a design range, and notice that all of these units are in metric. So what I can do is I can use the unit conversion package to convert from lengths. And the unit conversion package has all of the same unit conversions that MATLAB has, except it doesn't require an additional package within the aerospace toolbox. You can just use FAST without having to worry about any additional toolboxes installed in MATLAB. So you'll notice that we have a lot of convert velocities and convert lengths along this specification file. And it's important to note that you don't need an extra package to do it. It's all within the unit conversion package. At any rate, back to the performance parameters. So we have the takeoff cruise speeds and altitudes, the design range, which is required, so you must provide it, and then also a maximum rate of climb. From the aerodynamic side of things, we ask you, if possible, to provide lift to drag ratios for climb, cruise, and descent. Takeoff and landing use a simplified analysis right now, so we don't need an L over D for those. And also a wing loading. So one thing that FAST does not do is that it does not create constraint diagrams. So the user prescribes the point performance parameters ahead of time, which are either the thrust to weight and power to weight ratio and the wing loading, in addition to the required variables that you provide here. If you don't give us the wing loading or the thrust to weight ratio, we'll use the regressions to come up with something, but it may not be exactly what your aircraft needs. Moving on now, we've covered the aerodynamics, so now we're getting into the weights. So we have our MTOW, maximum takeoff weight, the block fuel, the landing weight, if you know it, the battery weight, again, if you know it. FAST will size the battery for you, so this is an optional input. The electric motor weight and the electric generator weight, again, FAST will size all of these for you, so all of these inputs are optional. If you know some of them, that's great because it helps FAST converge on a design quicker. Now we'll get into the propulsion specifications. So the one thing you'll need to do is specify the propulsion system architecture. And we have quite a few that are shipped with FAST. There's a conventional architecture, which is just running on gas turbine engines, a fully electric, which runs only on batteries and electric motors, a turbo electric, both fully and partially turbo electric, as well as a parallel and series hybrid. You can specify other architectures by setting propulsion.arc.type to O, and in a later tutorial, we'll talk about how you can create these other propulsion architectures. So there's a bunch of inputs, again, in this README file that pertain to the propulsion architecture. We'll get to those in a later video because we want to keep things simple for right now. And since I'm using a turbofan aircraft, as specified up here with the aircraft class, I'm going to provide a thrust to weight ratio instead of a power to weight ratio. Now you'll notice here, I've also prescribed the total sea level static thrust. So we have a thrust to weight ratio, a static thrust, and an MTOW. Now, if you are smart and remember what happened in the last video, we got a warning when we first ran FAST saying, you've provided a thrust to weight, a thrust, and an MTOW. The system's overspecified. So what it does, it'll actually neglect this thrust.SLS value, and it'll compute the sea level static thrust based on the thrust to weight ratio and the MTOW that you prescribed. Additionally, you can prescribe the propulsive efficiency, the number of engines, and you also need to specify an engine from the engine model package. We're going to talk about these in a later video, especially how to create your own engine specifications. But all of the engines that exist right now can be found in engine model package and the engine specs package. And if we open the one up that we're looking at right now, the CF348E5, you can see it has a similar function header. And towards the bottom, it'll have information about the type of engine it is and the applicable aircraft. So if you see an engine, if you're looking for an engine to fit your aircraft, definitely take a look at the documentation to see which ones may be appropriate. And again, we'll go through the engine model in a later tutorial. Right now, we're going to focus on just the aircraft specifications. So you'll notice that I just put the engine model package.engine specs package.myengine in here. And that's how this aircraft specification will connect to the engine specification. And then next up is the power specifications. So here I'll provide the specific energy of the fuel and battery I'm using, along with a number of efficiencies for the electric machines, if it's an electrified aircraft. So even though we're flying a conventional aircraft here, I just included some of this stuff so you know what it looks like, but leaving it as NAN is totally okay too. Now, since we are flying a turbofan, I am not going to give a power to weight ratio. I'm going to leave that as not a number, along with the electric motor and electric generator, because again, we're flying conventionally. Next up is the number of cells in series and in parallel for a battery. So when you're flying an electrified configuration, there's actually two different levels of detail in the battery that you can choose. One of them is to leave cells in series and in parallel as NAN, along with the beginning state of charge as NAN. And in this case, FAST will only size the battery for the energy requirements. However, if you do provide the number of cells in series in parallel and the beginning SOC, or state of charge, FAST will not only size the battery based on the energy, but also based on making sure that the state of charge doesn't fall below some minimum limit. And we set that internally in FAST to be 20%. So right now we're going to leave these as NAN, but if you're flying a hybrid electric aircraft and you need a really detailed battery analysis, I would recommend changing these to have some sort of numerical value. If you're flying a hybrid electric aircraft and you're just trying to get a quick and dirty approximation, then maybe you can leave these as NAN and just size the battery for the energy only. So now that we've gone through the power specifications, the last thing we're going to do is go through the mission analysis settings and some other settings in FAST. So the takeoff, climb, cruise, and descent segments can have a variable number of points in them. So we allow the user to set those here if you'd like. Otherwise, you'll use default settings. Notice that we don't have landing here, and that's because landing is a very simplified analysis. So we only use 2 points in landing at all times. Additionally, depending on how quick you want FAST to run, you can specify the number of iterations as well as a tolerance when converging on an operational empty weight. Lastly, you can prescribe whether you are doing an on-design analysis or an off-design analysis. On-design analysis means that you are actually sizing the aircraft. So we're going to size the aircraft both for its OEW and its energy sources, how much fuel, how much battery you need to carry. In an off-design, if you changed settings.analysis.type to -1, then we would only look at the aircraft performance. So we would no longer size the aircraft. The OEW would be fixed. All the component weights would be fixed. The only thing that would change is the fuel required to fly the mission or the battery required to fly the mission. And then lastly, if you want to plot your mission history, you can set this variable to be 1. The default in fast is to not plot it. So we can either set this as 0 or not a number, and we set it as not a number in this case. So hopefully this provided you a quick look at all of the different values that the user can input into fast. And you'll notice that a lot of them were set to NaN here, but we still ended up converging on a design in the previous video. So as you're building up your aircraft models, we definitely recommend figuring out how many inputs you actually need to provide and how many inputs you can let fast figure out with the regressions. And you'll see very quickly that the regressions are pretty powerful, especially when you don't know much about the aircraft besides the top level requirements. So with that, we would like to thank you for joining us in this video. And in the next video, we will talk about prescribing a mission profile. So this video is all about figuring out how to design an aircraft and provide those specifications. In the next video, we'll talk about prescribing and creating mission profiles. So thank you for listening, and we'll see you in another video.